All right, ladies and gentlemen, you are about to begin Ralston Valley High School's AP Chemistry Lecture Series, Chapter 22, Lecture Number 1 on Organic Chemistry. Let's begin. So here we are in Chapter 22, studying organic chemistry. Organic chemistry is generally the study of carbon-based compounds and their properties. Now, carbon being a group 4 element, a carbon group element with 4 valence electrons, has the ability to form incredibly complicated chain molecules. And as such, chemists sometimes dedicate their entire lives to studying specifically the chemistry of organic chemistry, that is carbon-based chemistry. We, in our AP chemistry class, are just barely going to scratch the surface of this particular topic. If you go on to study more chemistry in college, it's possible you'll be taking multiple semesters of organic chemistry. So note here that our one little chapter on organic chemistry is only a brief introduction to what is an incredibly vast field of study. Now, that being said, the reason why I would like you to have an understanding of organic chemistry, or at least basic organic chemistry here in AP Chem, is because oftentimes the AP test will actually use organic molecules as a means for asking you questions about a variety of other topics in relation to how they apply to these organic molecules. So being able to identify some simple organic molecules and their properties is a really, really useful skill that'll help you to predict the behavior of these chemical species. So that being said, we're going to start off with the very basics. The basic molecule of a hydrocarbon is what's referred to as an alkane. An alkane is what we call a saturated hydrocarbon. And by saturated, we mean it has all single bonds, and those single bonds are generally going to be between carbon atoms and hydrogens or carbons and other carbons. So again, saturated means essentially the molecule has already got all the possible number of hydrogens bonded to the carbons that it can possibly hold. The name of an alkane molecule is based upon the number of carbons that are chained together to form the backbone of that molecule. And we've given you here a list of the names of the first 10 alkanes here. And we'll go through and get the formulas of these different alkane molecules. Starting off with a familiar one here, that is methane. Methane is the primary component of natural gas, and its chemical formula is CH4. We can have a look here real quick at the Lewis dot structure for a methane molecule. We see we have the central carbon atom and 4 hydrogens bonded around the outside. So we have methane here, CH4, with 2 carbons in the chain. Again, have a look at this Lewis dot structure, 2 carbons in the chain. We end up with the formula here for ethane, a 2-carbon alkane. The chemical formula there would be C2H6. And a 3-carbon chain is referred to as propane. So propane with 3 carbons, and around the outside we will see we can fit 8 hydrogens around the outside. We end up with that formula C3H8. Now I'm just going to go through real quickly here for the remainder and give you the formula of these higher number of carbon alkane molecules. And then we'll discuss kind of a generic formula we can use to determine the formula of any alkane based upon the number of carbons that are present. So propane again, C3H8, found in propane grills. Butane, often found in say butane lighters. Butane has the chemical formula C4H10. Pentane, pent, a prefix which means 5. That is a 5-carbon chain, so C5H12 for pentane. Hexane, like a hexagon, 6 carbons in the chain, so C6H14. Heptane is C7H16. Octane, the primary component of your gasoline, is C8H18. And then nonane is C9H20. And decane is C10H22. So those are the first 10 alkanes here for our saturated hydrocarbons. And if you have a look at a couple of those Lewis dot structures we drew right there, have a look in particular at, say, ethane and propane. Looking at those Lewis dot structures, you see if we kind of imagine these as flat molecules, they're certainly not because these are all tetrahedral arrangements of these atoms, but if we imagine them as flat molecules, you see that in our carbon chain, each of the carbons is bonded to a hydrogen both above and below it, and then the carbons on the ends are also bonded to another hydrogen each. which means if we wanted a generic formula for our alkane molecule, we would take the number of carbons and then multiply that number of carbons by 2 to get the number of hydrogens, plus adding additional 2 hydrogens, accounting for those 2 on the ends as well. So the generic formula then for an alkane molecule is Cn, where n is the number of carbons, H2n plus 2. So with that generic formula now, I could just take any hydrocarbon, as long as it's a saturated hydrocarbon, and determine the formula. If you imagine something like, say, paraffin wax has generally around 25 carbons in the chain. So we might see something like paraffin wax as being a molecule C25H2n plus 2 would be 25 times 2 is 50 plus 2 gives me C25H52 for paraffin wax. So now I have a means of determining a generic formula of any alkane. Please do commit these first 10 alkane names to memory here. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And we'll move on now to some more complicated organic molecules. Now, whereas an alkane molecule was a saturated hydrocarbon, that was a hydrocarbon chain that had all single bonds, essentially we couldn't add any more hydrogens to it than already were present, we are going to look next at what we refer to as the unsaturated hydrocarbons. An unsaturated hydrocarbon which contains a double bond is referred to as an alkene molecule. That ending is ENE. And likewise, an unsaturated hydrocarbon which contains a triple bond, we refer to that as an alkyne. That is the suffix YNE. So let's go ahead and, with those definitions, look at just a couple of alkenes and alkynes. We base the name of an alkene or an alkyne upon the base name for a saturated hydrocarbon. That is, we start with the alkane name, and then we change the suffix from ane for the alkane to either ene or ine, respectively, for alkenes and alkynes. So whereas a saturated 2-carbon alkane chain is referred to as ethane, a 2-carbon chain which contains a double bond between the carbons, we would refer to that as ethene. And ethene has the chemical formula, as you have a look at our Lewis dot structure here, as C2H4. Likewise, if we had a 3-carbon saturated chain, we would call that molecule propane. If we add a double bond between 2 of the carbons there, you'll note here that we end up with a new structure here, whose chemical formula would be C3H6. And to name that species, we would again take the name of the alkane, which was propane for the 3-carbon chain, and we change the suffix to ene, meaning we call this one propene. So C3H6 is propene. Now you notice here we got a pattern kind of developing here. Ethene was C2H4, propene C3H6. That means that the generic formula for any alkene molecule that has just one double bond in it, we would give that the formula of CnH2n. That is, there's always twice as many hydrogens as there are carbons in an alkene molecule. We can go through the same process for those alkynes. Again, remember those alkynes contain a triple bond. A 2-carbon alkane, as we mentioned before, was called ethane. But if we change that single bond in the saturated hydrocarbon to a triple bond in the alkyne molecule, we end up with a new formula, which is C2H2, and we refer to that one as ethyne. Likewise, thinking about a 3-carbon alkane, which was propane, if we change it so we've got a triple bond between 2 of the carbons there, we end up with a new structure here for our 3-carbon alkyne, and the formula of that 3-carbon alkyne is C3H4, which is the chemical formula for propyne. And just like with the alkanes and the alkynes, we can give kind of a generic formula for an alkyne molecule. We take the number of carbons and we double them, and then subtract 2 in this case to get the number of hydrogens which would be present. So our generic formula for an alkyne molecule would be CnH2n minus 2. And again, that only works if you have just one single triple bond in the molecule. All right, so we now know how to name our basic hydrocarbon chains, but as it turns out, because of the flexibility that is afforded to carbon by its 4 valence electrons in terms of the number of bonds which it can form, we don't have to just stick to straight chain molecules. Oftentimes, we'll branch off of those straight chains, creating much more complicated and complex molecular structures. And that's what we'll have a look at next. Now, as we just mentioned on the previous slide, we now know how to name the straight chain hydrocarbon, alkanes, alkenes, and alkynes. But one of the amazing things about using carbon as the backbone of our molecules is that because carbon has those 4 valence electrons, it can form up to 4 bonds with other species, and they don't always have to be hydrogen. We can bond carbons to other carbons, and as such, we can form enormously large branched molecules off the main trunk of the molecule. Now, those side chains, or kind of side branches that we see come off of the main branch, we refer to as alkyl substituents. It's essentially sticking a chunk of carbons branched off of the main one, but we're going to base that chunk name off of the names of the alkane molecules based upon the number of carbons in those branches. So have a look here. We're going to go ahead and have a look at the structure of some of the most basic alkyl substituents. A 1-carbon alkane molecule is referred to as methane. That is a CH4 molecule. But imagine instead of having one of those hydrogens in a methane molecule, if instead of a hydrogen there, what if I just had a larger branch of an alkane coming off of that place where the hydrogen had been? In that case, we would end up with essentially a little branch with 1 carbon in it. And whereas the name of the alkane was methane, to name the branch, we're going to call that branch a methyl branch. That is methyl. So a methyl branch is a 1-carbon branch off of the main chain. Likewise, if I have a 2-carbon branch, I will name it based upon the 2-carbon alkane's name. A 2-carbon alkane was named ethane, so a 2-carbon branch off of a main chain would be referred to as an ethyl group or an ethyl substituent. Same sort of logic there. If I have a 3-carbon chain in a straight line there, we would refer to that based upon the name of a 3-carbon alkane. 3-carbon alkanes are propane, so a 3-carbon straight branch would be a propyl substituent. Now, here's where it gets a little bit trickier. If I attach my 3-carbon chain off of the main branch, I could attach it to the first carbon in the chain, which would give me 3 carbons in a row. Or alternatively, I could attach my 3-carbon chain to the central carbon of the 3-carbon chain. And in that case, we refer to that as an isopropyl chain or an isopropyl substituent. So depending upon whether you're attached to the end carbon or to the central carbon, that changes the name of our alkyl substituent from a propyl group to an isopropyl group. And here's where things are going to get really messy, and you note here that the more carbons in there, the more branching that can actually occur. So a 4-carbon alkane is called a butane molecule. That would imply, therefore, that a 4-carbon chain would be referred to as a butyl substituent if it branches off of the main branch of the hydrocarbon. Now, because we're dealing with such complicated looking molecules at this point, we need to go ahead and simplify our diagrams so that we don't have just hydrogens all over the place causing lots and lots of confusion. So for the diagram we're about to draw right here, every vertex point of the diagram I'm going to draw represents a carbon atom, which is as saturated as possible at that given point. So again, if you have a look at this particular vertex point on this diagram right here, that represents a carbon, which is bonded to one other carbon here. And we're going to go ahead and assume then that the carbon is as saturated as possible there again. That is, it will have 3 hydrogens bonded to it as well. So every place where we see a vertex along these diagrams, again, is a carbon as saturated as possible for its given point. Now again, a butyl group would be if we attach it to the end carbon of that 4-carbon chain. But there's multiple different ways we could attach a 4-carbon chain to our main branch of the molecule. So to name the rest of these, we're going to look through the rest of our butyl groups here. A sec-butyl group is what we get when we end up attaching a 4-carbon chain by the second carbon in the chain, which makes sense. We get sec-butyl. An isobutyl group is a little bit trickier here. An isobutyl group is going to end up, if you look at it here, attaching the 4-carbon chain to 2 carbons in a row, and then we're going to have carbons branched off of that second carbon in either direction. So this would be referred to then as an isobutyl chain. And then for our last possible permutation of this 4-carbon grouping, we end up with a 4-carbon side chain here in which there is 1 carbon attached to the main chain, and then that carbon itself has 3 other carbons attached to it as well. We refer to that as a tert-butyl group, which stands for a tertiary carbon. That is, that carbon that's attaching to the main group is attached to 3 other carbons as well. So again, the complexity of the branches increases with the number of carbons present in it. So please again note that these structures are named based upon the number of carbons in the chain. For our purposes, we're going to teach you a little bit about how to name these more complicated branched molecules, but for the most part, I just want you to recognize that if you get to college level chemistry and organic chemistry in particular, you're going to be spending weeks and weeks and weeks learning how to name organic molecules. So this is literally just scratching the surface here. So have a look at these structures, commit the easy ones to memory, but then just recognize that there are rules we'll go over to govern naming the more complicated structures. All right, now let's put a couple of ideas together here on this next slide. What we're going to do now is name a branched alkane molecule. So again, an alkane molecule is a saturated hydrocarbon, but we're going to start putting branches off of the main chain. So when we name a branched hydrocarbon, the base name of a branched hydrocarbon is always going to be derived from the longest continuous carbon chain within the molecule. Now, you got to be careful here because sometimes this can be a bit tricky. Have a look at the molecule which we have diagrammed on the right-hand side of our page right here. It could be very, very tempting to look at that molecule right there and say, well, I see where the longest chain is there. There's a straight chain running from left to the right with 1, 2, 3, 4, 5 carbons in it. So this looks to me like a 5-carbon chain. But that being said, be very, very careful, because if you're trying to do it that way, you're treating this molecule as a 2-dimensional molecule. But remember, each of those carbons there is bonded to 4 other things. That is, each of these exists in a tetrahedral arrangement. This is not a 2-dimensional molecule. This is very much a 3-dimensional molecule with 109.5 or so degree angles between all of those bonds in those tetrahedral carbons. So recognizing that, something that looks like a straight chain as it's drawn isn't really a straight chain at all, and something that looks like a 90-degree turn in the molecule isn't a 90-degree turn at all. The actual longest straight chain here is actually 1, 2, 3, 4, 5, 6 carbons, recognizing that those angles that we see on this page really don't represent the real actual angles of the molecular geometry in real life. So this looks to me like a 6-carbon chain with a little branch off the side. Now, once you've identified where the longest chain is, the next step is to number the longest chain. And we always start our numbering in the longest chain by giving the carbon closest to the first substituent the lowest number possible. So I could number this 6-carbon chain either 1, 2, 3, 4, 5, 6 in this direction, or backwards 1, 2, 3, 4, 5, 6 in the other direction. But you notice that going from the carbon that's drawn down below here, moving up and then to the left, this sequence of numbering 1, 2, 3, 4, 5, 6 puts that side chain CH3 grouping, that methyl group right there, on carbon number 3. Whereas if I started numbering on the left, that would put the side chain methyl group on carbon number 4. So we want to give my side chains the lowest possible numbering system possible, which means I'm going to start my numbering with the bottom carbon right there and number accordingly. And when you then name, we're going to give the position of each substituent a notation to show which carbon the branch comes off of as we name the molecule as a whole. So to name this example molecule we've drawn for you here, I recognize again that I have a 6-carbon chain, which means the base name of this is going to be a hexane. And on that hexane, on carbon number 3, there is a methyl group. So I'm going to give this a notation here. I'm going to call this 3-methyl The 3 again noting not to the number of methyl groups, but to the position, which carbon it is on. And then I'm going to name the alkane chain after that. This is 3-methylhexane. So there is an example of a branched hydrocarbon molecule. Now, a couple of additional things to note here on naming these branched alkane molecules. Because carbon is so flexible in its bonding, we can bond these carbon atoms sometimes not in a straight line, but instead in a ring. Should you come across a ring molecule, as in terms of a ring alkane, generally we use the prefix cyclo as the prefix for ring structures. And we name the molecule as we would for any alkane based upon the number of carbons in the ring itself. Now, please be careful to note here that the formula of a cyclic alkane is not the same as the formula of a straight chain alkane. A straight chain 6-carbon alkane would be hexane, which has the chemical formula C6H14, but a ring 6-carbon alkane only has 12 hydrogens attached to it, so it has the formula C6H12. So whereas hexane is C6H14, this molecule we've drawn right here is actually cyclohexane, whose formula is again C6H12. If we have substituent or side chains that come off of the main ring, I will name those, again, according to the rules we gave you on the previous slide, by numbering the carbons in the ring in a manner that puts the side chains on the lowest number carbons possible. So for this example right here, again, we have a 6-carbon ring, which means that this is a cyclohexane molecule. But you'll notice we have 2 substituent groups there, that is 2 methyl groups, and I'm going to number those on carbons number 1, 2, and 3 there, so 1 and 3, which means this particular molecule is actually going to be referred to as 1,3-dimethyl, di being a prefix there, which means 2, and then the name of the ring is cyclohexane. So this is 1,3-dimethyl cyclohexane. Now note there, I gave it the carbons number 1 and 3 right there. I just as easily could have numbered the carbons the opposite direction, making this one carbon 1 and this one carbon 3. But really, because this is a symmetrical molecule, it doesn't really matter how I do that. It's really the same either way. I haven't really changed my molecular structure by changing my carbon numbering system there. All right, so again, ring molecules get the prefix cyclo. And again, if we have substituents, number them in the ring, number the carbons in the ring to put those substituents on the lowest number of carbons. Now, another quick note here about these branched alkanes. Sometimes you'll notice here that as we get more and more and more complicated shaped molecules, we've got all sorts of carbons and hydrogens all over the place. As we saw just a couple of slides ago, sometimes to simplify a drawing of an organic molecule, we might omit the presence of hydrogens in our drawings and even omit the presence of carbons, showing each one of the vertex points along the diagram as a saturated carbon. So essentially, if I look at this drawing that's right here, where I see any bend that is a vertex within this molecular drawing right here, every one of those bends represents a place where there is a carbon, and that carbon is attached to as many hydrogens as you could fit there, saturating the carbon. So for this carbon right here, I would see that it has a total of 2 other hydrogens attached to it. So it really represents a point there where there is a saturated carbon. This can greatly simplify your drawings, but again, it might be useful to you as you're just getting used to drawing these things to again draw in your carbons where they are to figure out exactly what the formula of this species is going to be. Now, looking at this particular structure, we might as well go ahead and name this thing. In terms of the longest carbon chain which is present here, I note a carbon chain that has 1, 2, 3, 4, 5, 6 carbons in a row right there. So this looks to me like a 6-carbon chain right here. And you'll notice that if I draw it that way, I only have 1 methyl group coming off of that carbon chain. And as I've numbered it, starting to put that side chain at the lowest number possible, that would put that onto carbon numbers 1, 2, 3 right there, which implies, therefore, this thing right here is really a diagram of 3-methylhexane. All right, so we've now seen those simple ring molecules, those cyclic alkanes, we call them. One thing I want you to be on the lookout for, because it's a very, very common kind of base for building more complicated organic molecules, is what we refer to as a cyclic unsaturated hydrocarbon that we refer to as an aromatic hydrocarbon. The simplest of those aromatic hydrocarbons is a molecule called benzene. You also hear it referred to as a benzene ring. A benzene ring is a 6-carbon cyclic hydrocarbon where there are alternating single and double bonds drawn in your Lewis dot structure. But be careful here because it looks like this thing has alternating single and double bonds, but recognize that this is really just one of the resonance structures we could have drawn for benzene. It would be just as valid to have drawn the Lewis dot structure with the double bonds and single bonds in opposite positions to one another, which really means we essentially have electron density of around 1.5 bonds worth of electrons between each of those carbons. So again, it's not that some of those are double bonds and some of them are single bonds. It's really that we have resonance occurring in this instance right here. So a 6-carbon cyclic unsaturated hydrocarbon where we have 3 double bonds worth of electrons present in the ring is referred to as a benzene molecule. A derivative of benzene is essentially methylbenzene here. The common name for methylbenzene is called toluene. So watch out for benzene and toluene. They often go more frequently by their common usage names than they will by systematic names in naming systems. All right, and I think something you're going to find here is that more often than not, the best way of learning organic nomenclature is to just go about starting to name some compounds rather than trying to figure it out based upon theory alone. So let's just go ahead and start working some example problems right here. I'm going to ask you in example number 1 here to draw the following branched alkane molecules, the first of which is 2-methylpentane. Now again, following my rules right there, I recognize that the base of my molecule is going to be a 5-carbon chain based upon that alkane name of pentane, pent like a pentagon. So I'm going to go ahead and start by drawing 5 carbons in a row right there. And the substituent group that I have on my pentane molecule, I see there has that prefix methyl, and again, meth refers to a 1-carbon substituent chain. So that implies, therefore, I'm going to have a single carbon chain off of the second carbon in my 5-carbon alkane chain. So again, putting a carbon right there, I could then saturate this by drawing hydrogens all around the outside, which gives me now that molecule 2-methylpentane. Now again, you don't always have to limit yourself to just putting one single side chain off of one of your main branches. You could always have more complicated molecules that we could imagine. So have a look at this next one right here. This next one is called 3-ethyl 3-methyl octane. So again, the best sequence to go in here is to start with your longest chain. That octane name tells me I have as my longest chain an 8-carbon chain. And then the 3s, again, refer not to the number of these things, but to the number of carbon that they are branched off of. So on the 3rd carbon, it looks to me like I have 2 separate chains coming off of that 3rd carbon, one of which is an ethyl group, that is a 2-carbon side chain, and one of which is a methyl group, that is a 1-carbon side chain. So having now put my side chains onto that 3rd carbon, I can now go ahead and saturate the rest of those carbons on there by filling them in with hydrogens wherever possible. And this gives me, therefore, the structure for 3-ethyl 3-methyl octane. Now note in the name there, the sequence in which we name our substituent chains doesn't go based upon the number of carbons, it goes based upon the alphabetical ordering of the name of the substituent chain. That is, ethyl groups come before methyl groups because E alphabetically comes before M, not worrying that ethyl really has more carbons than a methyl. So 3-ethyl 3-methyl octane. All right, and now we've got a mess here. This next one here is 4-isopropyl 2,3-dimethyl heptane. So this thing is a kind of a beast. So have a look here, again, starting with the name of the main trunk of this molecule, that is heptane. Hept is the prefix which stands for 7. So we now have a 7-carbon long chain for my main branch. And then I've got 3 different substituent chains coming off of that. On carbon number 2 and 3, I have methyl groups. The 2,3-dimethyl means that on carbons 2 and 3, I have a methyl group each on those carbons. That is a single 1-carbon side chain on each of those. So that takes care of my 2 methyl groups. And then on carbon number 4, I've got the isopropyl group. Again, remember propane is a 3-carbon chain, which means a propyl group is a 3-carbon side chain. And that prefix iso there means that my side chain branch there is actually coming off of the central carbon of that 3-carbon chain there. So on carbon number 4, I've got that isopropyl group present right there. And then I can go through and saturate the remainder of my carbons present right here. So I've got 4 isopropyl, 2,3-dimethyl heptane. And again, note there that it's important which of the carbons I have labeled as carbon number 1, because we always want to put those substituent chains coming off of the lowest number of carbons possible. So again, this is 4 isopropyl, 2,3-dimethyl heptane, rather than what would have been an incorrect numbering scheme if I had called this thing 4 isopropyl 5,6-dimethyl heptane. So again, we always want to number it to put those substituent branches on the lowest number of carbons possible. So again, 4 isopropyl 2,3-dimethyl heptane. All right, so we've had you go through now and draw a couple of molecules given their names. Let's go now the opposite direction. Let's give you a Lewis dot structure for some of these alkane molecules and instead have you give us the name of these. So starting off with this diagram on the left. This one on the left right here, you see that the longest chain present here is a 1, 2, 3, 4 carbon long chain. Now note, it doesn't really matter here if I'm numbering it as this one as carbon 1 or this carbon as carbon 1, because regardless, I'm going to end up with the same name either way. Really, either of those can count as carbon 1 in this molecule. So again, I can number my carbons, carbon 1, 2, 3, and 4. And now I can go ahead and look at the functional group, which is present as a side chain. Looks to me like I've got a 1-carbon side branch there, which is a methyl group present. And so I can go ahead and name this now as 2-methyl, and then my 4-carbon long chain right there gives me my name here. So this is 2-methyl butane. So 2-methyl butane for this particular molecule. Now, having a look at this 2-methyl butane right here, sometimes you actually refer to this, here referred to as just commonly methyl butane, because as it turns out, if I took that methyl group and placed it instead here onto what I've currently labeled as carbon 3, really what I've just drawn right there is the exact same molecule. That is still 2-methyl butane, because by moving the methyl group from this carbon to this carbon, all I've really done then is just change the position of which I'm going to label as carbon number 1, which essentially tells me then I could just rotate that molecule in three-dimensional space and end up with the exact same thing. So again, this would be referred to as either methyl butane or 2-methyl butane. Putting that 2 in there is going to add some clarity, but not really change anything about the actual structure of my molecule. So that again is 2-methyl butane. Now let's take a look at this thing, which is kind of a mess. This thing looks really, really threatening, but don't worry. If we apply our rules thoughtfully, we can come to a name using our system that we've devised here. Again, my first step is to find the longest chain of carbons present. And looking at this thing, it's certainly not what immediately comes to mind of a 5-carbon chain through the center there of 1, 2, 3, 4, and 5. Because remember, these are not just linear molecules right here. These molecules all have tetrahedrally bonded carbons again. It's also not that up and down chain there of 1, 2, 3, 4, 5, 6 I see, because again, what looks like a 90-degree angle really isn't a 90-degree angle. It's just a tetrahedral arrangement around that carbon, as all of them are. So if I look for the longest chain I can find here, recognizing that what looks like a bend really isn't a bend in the same sense that it looks drawn on there, I actually see a 9-carbon chain here, starting here with carbon number 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I've got a 9 carbon chain there, and I've numbered now my carbons within that chain. I chose to make the carbon on the right there, carbon number 1, because in doing so, I put more of my side chains on the lower number carbon 4 right there. Note that as I've drawn it this way, there is 2 side chains on carbon number 4 and 1 on carbon number 6. Whereas if I had reversed it and drawn the left carbon as carbon number 1, in that case I would have had only 1 side chain on carbon number 4 and 2 on carbon number 6. So I've labeled my chain now, and I recognize that this is going to be some derivative of a 9 carbon chain, which is nonane. Now I just need to give the positions and names of those substituent chains off the side. So looking at this right here, I note that I have a 2 carbon chain on carbon number 4. So we're going to go ahead and name this thing as 4-ethyl. And then I have 1 carbon chains both on carbon number 4 and on carbon number 6, which means I'm going to add to my name 4,6-dimethyl, and then the name of the long chain, which was nonane. So again, this thing is 4-ethyl, 4,6-dimethyl nonane. And again, the ethyl here is going to come first because ethyl alphabetically comes before methyl. So again, as long as we are careful and systematic about our naming system, even complicated looking molecules here, we can arrive at a meaningful name that would allow us to figure out what we're really talking about. All right, so here we come to kind of a cool problem. I've seen this show up on AP tests in the past here. What we're asking to do here is to draw a branched alkane given the name. But as it turns out, the original name of this particular alkane is incorrect. And after you've drawn it, I then want you to go through now and give the correct name for that particular species. So with the name they've been given here, this is 2,2-diethyl 4-isopropyl pentane. So as a starting point for drawing our molecule right here, I'm going to start with the name of the base chain here, which is pentane. Pent again is a prefix which means 5, like a pentagon. So I'm going to go ahead and draw 5 carbons in my base chain here. And off of that base chain, I'm now going to go ahead, I can just arbitrarily assign one side to be the lower number 1 here. I'm going to go ahead and start drawing my side chains. So on carbon number 2, I've got 2 ethyl groups coming off of that. That 2,2 refers to each of the ethyls on the same carbon position. And then the di prefix there tells me that I've got 2 groupings now of an ethyl group, which is a 2 carbon chain. So off of carbon number 2, I'm going to put 2 carbon side chains. And then on carbon 4, I've got here an isopropyl group. And again, a propyl group is a 3 carbon side chain, and that prefix iso there tells me that I'm not attaching to the end carbon, I'm instead attaching to the central carbon of that 3 carbon side chain. So a 3 carbon side chain attached at the central carbon to carbon number, let's see, that's carbon number 4, we've attached that to right there. And then again, I could saturate this thing by drawing hydrogens all around the outside, and we've got now a successfully drawn molecule right here. But now that I look at that thing, it becomes immediately apparent that this really isn't a pentane molecule. Because again, remember, the angles that are drawn on 2-dimensional paper don't correspond to the actual molecular geometry of this structure here. So really, if I look for my longest continuous chain right here, I can see that I can find a 1, 2, 3, 4, 5, 6, 7 carbon chain from this particular molecule right there, which means really this isn't a pentane, this is a heptane molecule. And in order to correctly get the name right here, I again need to figure out which carbon needs to be carbon number 1. You'll notice that if I number this carbon as carbon number 1, then my first side chain comes on carbon number 2, and that would give me the lower numbers there, whereas if I go in the reverse, I would put my first side chain off of carbon number 3. So I'm going to label this then as carbon 1, 2, 3, 4, 5, 6, and 7. And I'm just going to circle real quick here my 7 carbon chain right here, which makes it easier for me to see now the side chains that are present. Off of my 7 carbon chain now, I have 1, 2, 3 single carbon side branches, that is 3 methyl groups. And then over here off of carbon number 5, I've got a 2 carbon branch, which would be therefore an ethyl substituent group right there. So I'm now ready to name this thing right here, this big huge mess of a molecule we have drawn. Again, remember in naming, ethyl comes before methyl because it is alphabetical E before M. So that implies, therefore, this molecule is 5-ethyl and then 2, 3, 5 trimethyl, again, tri being the number of methyl groups that are there, and the 2 and 3 and 5 being the carbons they come off of, and then the name of my base chain, which again was heptane. So 5-ethyl, 2,3,5 trimethyl heptane is the correct systematic name of this particular molecule. All right, for our last examples here in this first introduction to organic nomenclature here presentation, we're going to have a look at naming a couple now of alkenes. Remember, whereas an alkane is a saturated hydrocarbon, an alkene contains double bonds. Now, treating that double bond just kind of like a place in the molecule where there's something interesting going on here, we can recognize that that double bond can exist in different places, and therefore we might need to name the position of the double bond to distinguish between different molecules that otherwise look very, very similar. So have a look at this first one on the left hand over here. On the left hand side there, we've got, it looks to me like a 4 carbon chain, and I'm going to label those carbons as 1, 2, 3, and 4 right there. And in naming that right there, I'm now going to want to name the position of where I see that alkene double bond occurring. So naming this thing, I'm going to call this one over here 1-butene, because the double bond is starting after carbon 1 and between carbon 1 and carbon number 2. So this again is 1-butene. Now contrast that to the central drawing right here. Again, this is still a 4-carbon chain. It's still an alkene because we still have a double bond. But now, rather than the double bond being between carbon 1 and 2, now it's between carbons 2 and 3, regardless of which one I name as carbon 1 on which side. So again, this one right here would actually be 2-butene. Now, more specifically, this one right here that I have drawn is called trans-2-butene, which refers to a particular type of structure called a cis-trans isomer that we'll talk about in one of our next lectures. But for the time being, I just want you to recognize the difference between 1-butene and 2-butene. Now, this third one over here is also an alkene molecule, but now I have not 1 double bond, but 2. And this is where the naming is going to get a little tricky. On this one right here, I have 2 double bonds. It's still based upon the 4-carbon chain of butane as the base, but now those double bonds come after carbon 1 and after carbon 3, which means I'm going to name this one here as 1,3, and here's where the name gets weird, buta, and then I'm going to put the prefix di before the suffix ene. The di again telling me there are 2 of those double bonds which make this thing an alkene. So this is 1,3-butadiene. And we've now named a couple of these alkene molecules. Let's do it now the other direction as well. I've asked you to name the structures. Now let's go ahead and draw the structure from a name. On example number 5, we have here 2-methyl-1-pentene. And this is a fairly straightforward problem right here. Pent is a prefix which refers to 5 carbons in the chain. So I can go ahead and draw a 1, 2, 3, 4, 5 carbon chain. And the 1 before the name of pentene tells me the position of my alkene double bond is after the first carbon. So I'm going to go ahead and throw in a double bond after carbon number 1 right there. And then all I have left to do then is to throw on my substituent side chain right there. That is my methyl group, a 1-carbon side chain, off of carbon number 2. So I can throw in a methyl group right there. I'm going to abbreviate it CH3 for my methyl group. And then I just need to, as much as possible, saturate the remainder of the carbons right there. So I can put hydrogens around the outside wherever possible, filling up the remainder of my bonding positions around those carbons. So again, I've now drawn for you here 2-methyl-1-pentene. So that is the basics of naming alkanes, alkenes, and alkyne molecules. We'll get into more complicated organic molecules, including some things that include things other than carbon and hydrogen on our next lecture. Thanks for watching.